Maybe not so much.
Yeah, I mean, I think the important thing is just the tests themselves. I don't think there is much more available public, right? I mean,
Yeah, the unit test, and I
Yeah, the
think
unit
Charles
test.
Ogby is going to talk about the unit, a certain
Yeah,
unit
yeah,
test,
yeah, yeah.
because that's everybody's using that same platform now. Yeah, but it's a good point. Is when you introduce changes like this, it's like they do cost money to mature and get up to the Class B level, and so that's why we need projects that have funding to be able to do this, or some independent money man. He's getting us money as we speak. So I'm going to skip Joe's for the minute and go in.
John,
Is he on?
I just called in when I saw you got to my section.
Oh, great. This is perfect. And we can hear you.
Good.
So
Good,
we're on
excellent.
your first slide. Just tell me when you tell me
I'm
when you
looking
want
at it
to.
on the YouTube, so we should be good to go.
Okay, there's a 30-second delay to edit anything bad I say.
All right.
All right, so go ahead and talk to the first.
Okay, so yeah, we when we started using CFS and thinking about this concept going forward of having lots of different apps from lots of different places and perhaps this community really growing and with a lot more things available. Looking at the Makefile system, we came to the conclusion that we're going to have a few issues to work through. And I outlined a couple of them here. And I think first and foremost, it's the two-part design of the Makefile. If you look at the classic Makefile system, there's what I refer to as an outer part, which is the Makefile that you actually execute that lives in the build directory. And that refers to an inner part that actually comes with the CFS application source code. And the problem there is that these two don't move together, right? So they come from different places. The outer part is generally part of your build, your deployment script, but the inner part comes with the application. Unfortunately, there's not a clear line of demarcation between the two. The two parts are actually fairly tightly coupled, where the outer part sets up a number of variables that the inner part uses, and there's kind of some back and forth there. So unfortunately, it doesn't really allow one to change entirely independently of the other. So we can go on to the next slide.
$20 seconds.
Yeah. So the other issue we kind of ran into is that it relies on this make depend target, that it relies on the user to actually run make depend, and that's the only thing that's going to generate the dependencies between C source files and header files. Also, the make depend is going to be difficult to extend to other types of dependent files without an explicit rule. So, for instance, when you get into the electronic data sheets type of setup where the header file is actually dependent on an XML file, and there's quite a few of those, and you're not going to want to have to spell those all out manually in a make file. You want those to actually be generated. The other issue we ran into with make depend and having to call that explicitly is that it can get out of date. As you change your source files, you might include other header files, and those other header files you might get a new version that includes some other header file. So really, they have to be updated with every build, but relying on that explicit make depend target, it doesn't always stay up to date. So that was another problem that we ran into. Third issue, and I just touched on this, is not readily extensible. So as I mentioned, having other types of dependencies, they're all going to have to be explicitly laid out in the make file and manually maintained. Also, by having this outer build tree, if you say want to go to a second CPU or a third CPU, it requires cloning all the files in the outer tree. So you end up with a situation where the total number of files that are part of your make system is going to grow exponentially, as you add another application, as you add another CPU, it's really a multiplier effect. And the same with a configuration. Like, so if I wanted to build the code for a full flight avionics simulator that has the correct processor and all the external components, then that would be one build. But if I had an alternative simulation, maybe a software simulation that utilized a different processor and a different environment, I would have to also clone my entire build tree and make those updates and have it build for the other processor. There's no way to have one set of make files and have it build for multiple different environments, at least not easily. So next slide, please. Okay. So the solution is to use more of think of it as a meta make file. Cmake is a tool that's been out there for quite some time, and it's fairly mature. A lot of scientific projects actually use it. I run into it all the time with math libraries and machine learning libraries and that type of thing. So it's fairly commonly used in those environments. What it really does is it's a tool to generate your make files. So instead of writing GNU make files from scratch by hand, this tool, given a set of more generic recipes, will actually generate the make files for you and keep everything in sync. It allows for a clearer differentiation of the information roles. What I'm calling is information roles. So there's kind of three of them in play, where you have how to build a specific application. You know, the source files that go into it and the binary file that comes out of it. So it's fairly generic in that regard. It's just a bunch of C files that are going to get turned into a .o file or .so file that'll be loadable. Then you have information that defines how to tune your build for a particular board or a particular architecture. So that's board specific, and it logically is kind of part of the PSP. So if you change to a different platform, though that information would change, but everything else can stay the same. And likewise, you have what I refer to as the mission-specific information, which is a collection of applications. You know, which applications I'm actually going to deploy on my target system, and the table definitions that go along with that. So any apps that have a table that would need to be customized for your application, that's all part of your mission-specific set. Now, the idea here is we want to be able to specify all of these independently so they don't step on each other, for one. So you can mix and match different pieces from different places and have the system still work. And we also want to make sure that they're reusable. The idea being is if I have a set of cross-compiler and tuning flags for a particular board, say if I'm building a Bone Black or some other embedded processor, there's a cross-compiler you can use and a set of compiler flags that you can use, and it doesn't matter what applications you're building. You shouldn't have to redefine that. So the idea is that can live with the PSP and be reused. And the same with the application recipes, is that it's a collection of source files producing a loadable object. We should be able to reuse those application recipes as much as possible. The mission-specific stuff is going to be more closely tied to the mission. That's less likely to be reusable. So with these three sources of information, you run your Cmake generator tool, and it produces a set of make files. And built into those make files is all the dependencies that are imaginable. I mean, it links all the C files to the header files. It links any derived header files to the original XML EDS object that they're from in the case of using an electronic data sheet build. And all the application recipes, even if you're building it from multiple CPUs, the same application recipe is used. There's just one recipe to build that application. It's just reused. And likewise, if you're using different PSPs on different CPUs, the application builds will be automatically tuned to the using the compiler flags, the correct cross compiler, the correct cross compiler flags as specified in the PSP. So it really consolidates the information that everything comes from one source, at least in these three information categories, and you shouldn't have to edit anything except your very mission specific part. So we can next slide. You can go on. All right, so just to give a quick overview of what a top-level Cmake build tree looks like, it should be fairly recognizable. We have the CFE, OSAL, and PSP. Those are actually kind of in the middle there. But the main thing I want to point out is those subtrees would literally be a clone or a subtree or a submodule checkout of the CFE source code. And while those may provide sample files, the sample files are really only to bootstrap you and to get you going with respect to your mission config and your platform config. The important thing is that you're not going to modify any of those files in place. The CFE, or the Cmake builds for the CFE puts extensive emphasis on leaving the source version-controlled source documents in place and not modified. So you retain full compatibility going forward. The problem is if you have to tune any mission config or platform config files and you tune them in their original locations, you're essentially forking the code, and when the next version comes out of any of these components, you're now on the hook to do a manual merge between your modifications and the original version. And obviously, if the original version is also updated, you're going to run into potential merge conflicts, and it tends to get a lot more complicated and a lot more manually involved. So by keeping the source code pristine, you should avoid any such merge issues going forward. And of course, you can diff if you happen to make your patches. If you find a bug and you make any local modifications, those diffs will work. So you could submit patches to the upstream, whatever group is managing that application that you're using. You should retain full compatibility. And all of your local mission configuration would be in a separate directory. In this case, it's the sample defs directory, such that it can be version controlled in your own repository, but it wouldn't interfere with your upstream subtrees or your subtrees that match to upstream projects. And the final thing to point out here is that the build directory contains no handwritten files. So that is 100% generated. It does not need to be version controlled. So when this is put into a version control system, the build directory is not included. The entire build directory is created when you run the build script. Next slide. Okay, so we touched on the electronic data sheets aspect of it a little bit. One thing to point out here is that the classic Cmake or the classic Make scripts will continue to be available in 6.5 and 6.6, 6.6 being our upcoming release. Also in 6.6, we are looking to add in the EDS, and that is it does make things a little more complicated because the EDS is generating some of the files, some of the C header files that are it's handwritten in the current version. So the proposed release, or the proposed approach here, is to include both, such that you can generate the files from EDS, which will then override the handwritten files, but will continue to support the existing Make simply by essentially checking in the output of the tool such that the classic make will continue to work for this release. But you definitely get some benefits by using the Cmake approach because you have all the dependencies in place. If you're using just the snapshot in the classic make and you change the EDS, there is no dependency there. The EDS won't be or the header file won't be regenerated from the EDS, so that change won't be propagated as it's supposed to. So definitely, if you're interested in using EDS, it is strongly encouraged to use the Cmake build scripts so that all the dependencies in the chain still works. Next slide. Okay, so yeah, integrating the EDS with the Cmake. So as part of the electronic data sheets, you can specify all of your APIDs for your various subsystems in an electronic data sheet. So for every app, you can associate an APID with it, and that's all done through the electronic data sheet XML schema. These are mission-wide, so that every CPU, every application sees the same numbers. And the dependency, again, is all generated by the Cmake. When you run the Cmake tool, it builds all those dependencies into the make files. And all of the actual C header files that applications can include are generated by the tools. The tools can also output